Most people step right over the one clue that under angled sunlight gives away a diamond fragment hiding in plain sight. It isn't the size, nor the color, nor even the crystal shape. It's the sudden, unmistakable flash of adamantine luster, brighter than quartz, sharper than glass, and gone in an instant if you blink. That brief flash, when the angle is just right, marks the difference between an ordinary river pebble and a fragment potentially worth thousands. In placer environments, especially in old riverbeds or glacial deposits, diamond fragments often lack the perfect octahedral faces collectors hope for. Instead, what remains are edge-worn, translucent to opaque chips that mimic quartz in shape, but betray themselves through how they handle light. Quartz gives a muted vitreous shine, almost waxy in dull conditions. True diamond, even in fragment form, punches above its size optically. Field geologists call it hard sparkle. Under natural light, this luster refracts and reflects with an intensity unmatched by other clear minerals in the same size range. Another early signal comes from handling. The moment a suspected fragment is picked up, its density, or more precisely, its heaviness for size becomes evident. While diamond's specific gravity, Sg, is about 3.52, quartz hovers around 2.65. That difference might sound slight on paper, but in hand, particularly when you've handled dozens of quartz fragments, a diamond piece will feel unnaturally weighty for its volume. The effect is subtle but learnable. Prospectors who train this intuition often recognize a good candidate before any test is run. However, the shape can mislead. Diamond fragments, particularly those weathered through fluvial transport, rarely maintain perfect symmetry. Edge abrasion can soften or even erase the characteristic triangular growth lines or octahedral terminations. What's left can resemble window glass, calcite, or tumbled quartz. This is where surface inspection becomes critical. Look for subtle growth lines, a greasy rather than glassy texture, and micropitting that reflects directional wear. These are clues to primary origin and transport history. Magnification helps, but isn't essential in the field. One trap is glassy slag or high-index industrial glass, which can mimic diamond's luster and occasionally exhibit similar density. Here, the lack of crystal habit is telling. While both glass and diamond fragments may be irregular, man-made slag lacks any internal structure. Real diamond, even in fragment form, may show directional striations, cleavage steps, or minute inclusions that suggest natural growth. Under angled light, even chipped diamonds may show crystal memory, ghosts of their original form that glass cannot replicate. Field confidence at this stage remains low without further testing. But these early visual and tactile cues, hard sparkle, weight in hand, surface growth textures, are often what separates those who keep walking from those who begin a test sequence. For those willing to pause and examine, the next indicator often isn't in the crystal itself, but in the company it keeps, indicator minerals in the surrounding gravel. The moment a candidate fragment shows promise in luster or weight, the next step is to separate signal from noise, and most of that noise is quartz. In gravel-rich environments, quartz dominates the visual field, often outshining rarer materials simply by abundance. But diamond fragments betray their identity early to a trained eye, not just in the way they reflect light, but in how they behave under the simplest field test: density, intuition, and comparative luster. Quartz, by far the most common clear to white mineral in alluvial zones, presents with a duller vitreous luster and a significantly lower heft. Experienced fieldworkers use an informal but remarkably effective approach. Pick up 10 pebbles of similar size, including the suspect, and weigh each in hand. Time after time, the diamond candidate will feel slightly heavier, even when chipped or rounded. This difference becomes even more apparent with repeat experience. The luster check, however, is more precise and less intuitive. Diamond fragments, regardless of their shape, exhibit adamantine luster when clean and dry. This specific type of luster is sharper and more metallic than quartz's vitreous sheen. Under direct sunlight, the difference becomes dramatic. While quartz disperses light softly, even almost hazily, diamond flashes back a pinpoint, high-contrast reflection. This quality holds even in clouded or slightly scratched fragments. The key is to tilt the stone slowly under consistent light, ideally sunlight or a strong white LED. If a sudden, piercing white flash appears and disappears as the angle changes, the candidate passes the luster check. In contrast, moissanite and some high-index glasses can mimic this flash. That's why luster must be paired with behavioral cues, how the stone interacts with weight, magnetism, and even sound. Tapping a diamond against a metal tool or ceramic plate produces a sharper, higher-pitched click than quartz or glass. Though subjective, this sound test has historical precedent in artisanal mining zones and can flag false positives or reinforce suspicion when combined with other traits. Still, errors happen. Clear calcite and topaz, in particular, can mislead. Calcite can sometimes exhibit a ghost of adamantine luster, but often betrays itself through cleavage, clean breaks along planar surfaces. Diamond rarely cleaves in this way during river transport. Instead, its chips tend to show conchoidal fracture or irregular breakage. Topaz has greater density than quartz and a respectable luster, but its habit is often prismatic, and its edges straighter. These comparative reads matter most when candidate fragments show no obvious crystal form. Tools enhance confidence but aren't mandatory. A jeweler's loupe or even a 10 times magnifier allows closer inspection of surface wear and microinclusions. Some diamonds, even in fragment form, hold tiny mineral specks or cloud patterns absent in quartz. When visible, these inclusions suggest natural origin and differentiate candidates from flawless synthetic or glass imitations. Two gravel bars 100 meters apart can yield completely different outcomes, one littered with quartz and garnet, the other hiding a diamond fragment just beneath the surface. The difference isn't luck, it's terrain logic. Understanding the geological backstory of a site is often the only way to explain why diamond fragments cluster in one area and vanish in another. And it starts with the pipes. Most natural diamonds originate from deep-source volcanic intrusions, kimberlite and lamproite pipes, that punch upward through the crust. These structures form narrow vertical conduits, often no more than a few hundred meters wide, but they serve as the only natural delivery mechanism for diamonds from the mantle to the surface. The problem: these pipes are rarely visible anymore. Time, weathering, and sediment cover them. So diamond fragments don't usually appear at the pipe. They appear downstream, often far downstream, scattered by water, ice, and gravity. That's where erosion vectors and sediment traps come in. Over thousands or even millions of years, erosion grinds away at exposed or shallowly buried pipes. As the upper portions weather, liberated diamonds, and crucially other associated minerals, enter the local drainage system. From there, the fragments behave like other heavy minerals. They move slower than lighter sediment, tend to settle in meander bends, behind obstacles, and in plunge pools. Ancient riverbeds, known as paleochannels, are often more productive than active rivers. These former watercourses were once primary transport paths for eroded diamond material, but have since been buried or diverted. Remote sensing and old topographic maps sometimes reveal these features, especially in regions with known pipe clusters like parts of Central Africa, Siberia, northern Canada, and Western Australia. In these zones, even subtle terrain depressions can signal an old channel, a buried opportunity. Where field access is possible, mapping slope breaks and terrace levels can guide where to dig or sieve. Diamonds, due to their density and size, often lag behind lighter material in sediment flow. On a macro scale, this means they collect in zones of low turbulence, inside bends, behind large boulders, or at sudden slope reductions. In old terrace layers above current river level, fragments may lie undisturbed for millennia, protected from seasonal scouring that wipes out newer deposits. If a fragment is found, the question becomes, upstream or downslope? In most terrains, the logic follows gravity and water. A single fragment rarely travels alone. The odds increase dramatically if the terrain has a known kimberlitic signature. Even without direct access to geological survey data, the presence of specific associated rocks, Blue-ground, serpentinized material, altered peridotite, can hint at nearby pipes. In some landscapes, like those of Brazil or Western Australia, erosion-resistant materials concentrate over time while lighter, reactive stones wash away. These residual soils, though less flashy, can harbor diamond fragments trapped in saprolite or ferrocrete, a soil-bound legacy of long-gone surface activity. Careful trenching or panning in these zones has uncovered industrial-grade diamonds, often with little else nearby to suggest their presence. A single diamond fragment is rare enough to raise eyebrows, but when it appears alongside certain minerals, it shifts from anomaly to confirmation. These silent companions, known as indicator minerals, don't just signal that you might be near a diamond-bearing source. They often pinpoint the exact erosion path from the hidden pipe to where you're standing. Among them, a few show up again and again in real discovery zones: pyrope garnet, chromite, ilmenite, magnetite, and more subtly, orange to green clinopyroxenes and spinels. When found together, they create a mineralogical fingerprint that prospectors have followed to the mouths of previously unmapped kimberlite pipes. The key is knowing what each mineral implies. Pyrope garnet, often with a deep purplish-red hue, resists weathering better than most silicates. Its presence, especially in rounded but undamaged form, suggests it traveled from depth and didn't get ground down in transport. When found in stream concentrates, often trapped in riffles or crevices, it points to ultramafic origins, the same geological roots as most diamonds. Chromite and ilmenite, both dark and dense, are harder to differentiate visually but can be quickly tested with a simple magnet. Ilmenite usually responds, albeit weakly, while chromite may not. Both can mimic common black sand until isolated under a hand lens or microscope. Their significance: both minerals form in association with diamond-stable mantle conditions. Chromite, in particular, remains stable at high pressures and temperatures and is commonly found in the deep roots of kimberlitic intrusions. Magnetite, while more ubiquitous, still matters, but only in context. Alone, it's a generic heavy, but when concentrated alongside the others, especially pyrope and chromite, it confirms an ultramafic story. This is where mineral ratios and co-occurrence patterns become more informative than any single find. Field testing these minerals doesn't require a lab. A standard neodymium magnet quickly screens for ilmenite and magnetite. Under magnification, pyrope garnet shows a distinct color zoning and high refractive index, often appearing brighter than common garnet species. A simple loupe or USB microscope can reveal these traits, especially in cleaned concentrates. For serious field verification, a portable XRF analyzer offers element-level confirmation, but even without one, grain, morphology, and color are strong initial indicators. When processing gravels, the best return comes from pan concentrates, batté methods, or a sluice with riffles optimized for heavy minerals. Sieve classification before panning, especially through 20 and 40 mesh, improves chances of recovery. Diamonds and their indicators tend to fall within specific grain size ranges, and sorting by size prevents loss in overflow or under-concentrated finds. But here's the catch: not all red garnets mean pyrope. Almandine, common in metamorphic zones, can look nearly identical to the untrained eye, so can andradite and spessartine in certain lights. The difference lies in color saturation, transparency, and inclusions. Pyrope is often cleaner, more vivid, and lacks the orange-brown tint seen in almandine. Still, visual ID is only a first step. More tests are needed for certainty. A good indicator suite sparks interest, but it's the first concentrated sample run that separates curiosity from actionable data. The goal at this stage isn't to confirm a diamond, it's to establish whether the terrain justifies a systematic grid or trenching program. That decision often hinges on what shows up in one or two buckets of classified material, passed through simple screens and processed by pan, batté, or sluice. It starts with collection. In a promising gravel bar, say, one where pyrope garnets and ilmenite grains have already appeared. A smart first pass targets the inside bend of a channel, the downstream edge of a boulder, or the toe of a gravel terrace. These zones act as natural traps for heavies. Sampling here means digging below the active flow line, ideally into the packed gravels 10 to 40 cm deep, where long-settled material hasn't been disturbed by seasonal scouring. Each bucketful of material must be screened before concentration. Using a nested sieve stacked typically 20 and 40 mesh, you isolate two main size fractions. 20 mesh holds particles, men above, 40 holds those between, men 0.85. Most diamond fragments and indicator minerals fall in these ranges. Material finer than 40 tends to be dominated by silts and clays, which obscure results and can wash away micron-scale indicators. Once classified, material is run through a gold pan or traditional batte, shaped to retain heavy minerals in the bottom curl. After careful washing and spiraling, what remains in the tail pocket tells the story. Bright red garnets, dull black ilmenite, metallic glints of chromite or spinel. Even 1 or 2 grains per pan load is meaningful if they show consistency across samples. Pay attention to the relative abundance. If pyrope dominates one pan and is absent from the next, you're either on a contact boundary or crossing a drift line. That variation becomes a map. Prospectors often carry a simple logbook or mobile app with GPS tags to track each sample's location, volume, sieve fraction, and indicator count. In higher stakes regions, that data can later justify permits, funding, or formal exploration filings. But even for small-scale operations, a 5-site first pass over a 100-meter stretch creates a basic contour of mineral movement. Equally important are the negatives. If a location yields no heavies, not even magnetite, it might suggest fast-flowing water recently scoured the site or that you're too far downslope. Either way, it's not just the finds but the gaps that shape your map. But not every good sample ends in success. Some gravels show dense indicators but still lack diamonds. Others yield a suspiciously good fragment, followed by weeks of nothing. That's the risk of false positives, and it usually becomes clear in the second stage of testing, when mineral response under UV light, thermal conductivity, and basic density checks begins to filter real diamond from clever imposters. At first glance, the fragment checks all the boxes. Adamantine flash, dense in the hand, found near pyrope garnets and ilmenite streaks. But then comes the ultraviolet test, and the response is underwhelming. Under long-wave UV light, instead of the expected bluish glow, the stone remains dim or worse, fluoresces an odd green or yellow. The moment triggers doubt. Could this be glass, moissanite, or something else entirely? This is where most would-be finders falter, placing too much weight on a single result. But the truth is, UV fluorescence alone is not definitive. It's just one tool among several, and its role is diagnostic only in the context of others. Fluorescence in natural diamond is common but variable. Around 35% of natural diamonds fluoresce blue under long-wave UV, but that still leaves a majority that don't. Conversely, some synthetic diamonds and high-index glasses exhibit strong fluorescence in colors atypical of natural stones. A yellow-green reaction, for example, might suggest a laboratory-grown specimen with nitrogen vacancy centers, or even a piece of slag glass doped for industrial tracing. So the response isn't a disqualifier, it's a prompt for the next test: thermal conductivity. In field conditions, thermal probes like the common diamond tester use a metal tip to measure how quickly heat dissipates into the stone. Diamond with extremely high thermal conductivity, tilde 2200 W/mK, pulls heat away rapidly, triggering a pass signal on the device. But moissanite with its own high conductivity, tilde 1200 W/mK, can also pass, depending on the device and calibration. That's where older testers fail. Newer dual-mode testers combine thermal and electrical conductivity checks. While diamond conducts heat, it's an electrical insulator. Moissanite, however, conducts both. A quick touch with a combined probe gives more clarity. If the stone passes thermal but also shows electrical response, odds favor moissanite. If it conducts heat only and remains electrically dead, diamond remains a contender. Yet there's one more critical test that trumps both tools: specific gravity via water displacement. This method, while less convenient in the field, offers hard numerical data. By weighing the stone in air and then submerged in water, or using a pocket scale and makeshift suspension, you calculate its density. Diamond averages G/cm3. Moissanite hovers around 3.2. Quartz, by contrast, is ~265. If your fragment lands within 345, 355 and the other indicators hold, the case strengthens. Still, the key is triangulation. No single test confirms a diamond in isolation. It's when luster, weight, thermal behavior, and density all align, and no red flags appear, that confidence rises. But even then, visual confirmation under magnification adds another layer. A loop can reveal doubling, a hallmark of moissanite, bubbles typical of glass, or cleavage patterns inconsistent with natural diamond breakage. Many false positives survive one or two tests before slipping up under scrutiny. That's why experienced fieldworkers never trust a single indicator. They look for consistency across the suite. A real fragment holds up under UV, thermal, density, and visual checks. Anything that falters gets isolated, logged, and often discarded. Once a candidate fragment survives initial testing, or fails but leaves behind compelling indicator traces, the next phase isn't guesswork, it's process. A structured, repeatable workflow distinguishes amateurs from serious field operators. The goal isn't just to find more fragments, but to understand their distribution, movement, and source probability. That starts with establishing a sampling grid and escalating from reconnaissance to systematic exploration. The process begins by plotting your initial find. Whether it was a single diamond-like fragment or a cluster of indicators, the coordinates and sample details must be recorded. In remote or low connectivity areas, a handheld GPS unit or offline mapping app suffices. For each sample point, include date, elevation, volume sampled, sieve fractions used, and test outcomes. A simple spreadsheet or logbook indexed by waypoint keeps the data actionable. From that origin point, a radial or grid sampling strategy unfolds. For alluvial terrains, a radial pattern works well, extending 10, 25, and 50 meters in each cardinal direction, collecting 1 or 2 buckets per station. For terrace or hillside zones, a grid makes more sense. A series of equally spaced transects, each with multiple sampling nodes. At each node, run the same process, screening to 20 and 40, concentrating with a pan or batte, and documenting the heavies present. To streamline, prospectors often use color-coded field trays to sort concentrate outputs. Red garnet, one tray; black metallic, another; anything clear with luster, set aside for tool testing. Over time, patterns emerge: zones with high pyrope density, lines where ilmenite thins, or sites where fragments cluster despite low indicator presence. These anomalies are vital. A zone with a diamond fragment but weak indicator sweep may reflect secondary transport, a redeposited layer from upstream erosion. For consistency, maintain a daily control test. That means sampling from a known negative site, an area already proven to contain no significant indicators, and running the same sieving and panning routine. If your control pan starts producing garnet, something in your method or gear is off, possibly cross-contamination or mislabeling. As data accumulates, the decision point comes quickly: scale up or stand down. If multiple stations yield matching indicators, say pyrope, ilmenite, and magnetite in repeatable counts, it's time to switch from hand panning to bulk sampling. That often involves running 50-100 liter loads through a controlled sluice, recovering heavies with miners' moss or magnetic traps, and inspecting under field scope or loop. These runs, while labor-intensive, provide statistically meaningful concentrate volumes that can justify core drilling or trench excavation. Record keeping becomes critical here. The value of any find, especially if you intend to sell rights, license data, or submit samples to a geological agency, depends on sample integrity. That means GPS-tagged photos, field sheets with real-time notes, and sealed sample bags with chain of custody labels. Lab-ready fragments should never be handled bare-handed or mixed with concentrates from other sites. And yet, even with perfect method, false positives slip through. That's why grid confirmation matters. A A single diamond-like fragment can appear due to glacial erratic transport or secondary redeposition. But if two or more appear in aligned sample zones, especially accompanied by a supporting mineral suite, then the terrain is telling you something. It had the look. The fragment, recovered from a dense concentrate below a serpentine boulder in a river bend, flashed hard under sunlight. It survived the hand luster check, felt heavy relative to its size, and passed thermal conductivity using a mid-range tester. Even the specific gravity test floated it squarely around 3.5 G/cm3, just within the diamond range. Field notes flagged the site as high priority. Over the next 48 hours, additional concentrates pulled 3 more fragments of similar appearance and size. The indicator suite nearby was textbook: pyrope garnet in 2 sieve fractions, magnetic ilmenite grains clustering at multiple nodes, and a subtle halo of chromite. All signs aligned. Then came the magnification. Under 10 times and then 30 times scope review, one fragment revealed a doubled facet edge, a slight repeating ghost line not visible to the naked eye. This is the telltale sign of double refraction, something natural diamond does not exhibit. The test was repeated with polarized light. Again, the internal features split, light bending twice through the crystal lattice. It was moissanite or something chemically close, a synthetic, high-quality silicon carbide fragment that had somehow found its way into the gravel field. This reversal triggered a halt. Every fragment was re-examined, and 2 more showed the same doubling. The 4th, cloudy and smaller, remained ambiguous. Thermal and electrical conductivity tests were rerun, this time with a dual-mode probe. The suspects all showed not only thermal conduction but electrical as well. They were imposters. The presence of moissanite in a natural alluvial context wasn't entirely impossible. Minute quantities do occur in rare ultramafic settings, but not in this configuration. The sharp-edged facets and polish suggested man-made origin. It's likely the fragments had entered the gravel bar from upstream dumping, possibly from tailings or industrial waste from synthetic gem cutting. The implications were immediate. The strong indicator suite remained valid, but the diamond-like fragments were not. The terrain still suggested potential. Kimberlitic material doesn't travel alone, and the presence of pyrope and chromite remained meaningful. But the find zone shifted categories, from a promising fragment site to an indicator-only anomaly, pending further confirmation. More importantly, the event exposed a common trap, assuming fragment truth based on aggregate testing. Each test passed, but none excluded moissanite. Only the optical check late in sequence revealed the reality. That's why trained operators delay definitive classification until all tests, including microscopic examination, are complete. Visual tests, particularly for double refraction, cannot be skipped or replaced. The setback, while frustrating, recalibrated the approach. The false positives didn't mean the terrain lacked value, only that the field signals needed confirmation before scaling. The team adjusted. New samples were taken from upslope, bypassing the likely contaminated stretch. The grid expanded laterally. It wasn't the fragment that changed the narrative, it was the garnet, or rather the way it responded under laboratory spectral analysis. After the field team's moissanite reversal, a set of pyrope garnets collected upslope were sent to a regional mineralogy lab for compositional profiling. Standard procedure, but the results weren't standard. The chromium content, specifically the Cr2O3 weight percent, was higher than expected for typical kimberlite-associated pyrope. The values averaged 8–11%, well above the threshold associated with G9 and G10 pyropes, which are geochemically linked to diamond-stable pressure conditions in the mantle. This was no longer just about fragments in gravel. The garnet chemistry suggested that the source rock, still hidden, might be part of a deeper, higher-pressure lithospheric root zone, and that shifted everything. The lab in question, a certified partner of a national geological institute, flagged the results for review, not because the values were odd, but because their match profile aligned with a class of lamproite intrusions rather than kimberlite. Lamproites, though rarer, are legitimate diamond carriers. Australia's Argyle mine, the world's most productive colored diamond source, was born from a lamproite. The implications for the site were enormous. Suddenly, previous assumptions had to be rechecked. The terrain had been read through a kimberlite lens, seeking traditional indicators, traditional erosion pathways, and classic pipe signatures. But lamproite behaves differently. It often forms irregular dikes or breccia zones, sometimes with altered margins that weather into soft, clay-rich soils. Its heavy minerals can masquerade as others, especially when only partially preserved. The team pivoted. Field notes were reinterpreted, and previously overlooked soft rock zones, once dismissed as decomposed schist or serpentine wash, were sampled again. This time, sieving targeted finer fractions. A surprising find emerged. small grains of phlogopite mica and clinopyroxene with color zoning, both consistent with lamproitic alteration halos. More telling was a shift in the indicator sweep pattern. Chromite gave way to richer ilmenite, magnetite faded, but the garnet counts held, and they clustered sharply upslope from the false positive zone. Repeat testing on these garnets confirmed elevated magnesium and chromium values, tightening the case for a lamproite origin. Yet the diamond question remained. No new fragments had surfaced. The original candidates were moissanite, so the team returned to trenching, targeting the transition zone where indicators clustered and soil color changed subtly from tan to buff gray, with greasy patches after rainfall. Here, careful excavation revealed clay-altered breccia fragments, soft, yet unusually dense, with embedded mica and black grains. One of those grains, separated under microscope, showed distinct crystal faces, sharp, irregular, partially coated. Once cleaned and tested, it passed every field check. No doubling, strong thermal conduction, no electrical response. Specific gravity measured 3.52. The fragment had no fluorescence, but that's not uncommon. Finally, spectroscopy showed nitrogen aggregates consistent with natural formation. The lab's verdict was decisive. Natural diamond fragment, likely altered from lamproitic origin, and small enough to explain its survival in surface gravels. This single, verified fragment, backed by garnet chemistry and terrain reinterpretation, shifted the project's status from speculative to strategic. The find location was now a confirmed lamproite indicator zone with proven diamond presence, previously unmapped, and potentially unique in regional geology. When a verified diamond fragment emerges from terrain previously dismissed as non-kimberlitic, the rules change, but the models still matter. Institutional data, gathered from decades of fieldwork across Australia, India, Russia, and parts of southern Africa, provides a framework not just for where to dig, but how to interpret what's found in lamproitic contexts. The key difference is shape. Kimberlite pipes tend to be vertical, carrot-shaped, and predictable in erosion. Lamproites are chaotic, bulbous, irregular, and often form breccia-filled dikes that erode differently and leave subtler clues. The Geological Survey of Western Australia published a series of lamproite case studies in the 1990s, including the Argyle Field. Their models showed that lamproitic diamond dispersion rarely forms neat downstream trains. Instead, fragments often concentrate in lateral fans or shallow depressions, just upslope from the actual source, sometimes due to soil creep or asymmetric erosion. This means that relying solely on the fragment's position can mislead the search. In the case at hand, trench data and indicator clustering were cross-referenced with historical lamproite dispersion models. The breccia horizon that yielded the confirmed fragment was located meters downslope from a shallow slope break, an innocuous ridge flanked by scrub. No visible outcrop. No alteration halo visible from satellite or aerial surveys. But the ground texture changed, softer underfoot and slick after light rain. Institutional profiles flagged this as a textbook indicator of lamproitic subcrop, especially when paired with high chromium pyrope counts and phlogopite-rich finds. Grid sampling was reconfigured accordingly. Instead of radiating from the fragment site, the team laid transects perpendicular to slope fall, targeting the contour just above and just below the slope break. Sample pits every 5 meters, with sieving to 40 mesh and magnetic separation, revealed an increasing presence of pyrope and clinopyroxene upslope. More breccia fragments appeared, light gray, vesiculated, and mica-flecked. At 12 meters upslope, trenching revealed a subsurface vein of altered rock, tilde 3 meters wide, running at an oblique angle to slope direction. It wasn't an obvious pipe. It was a dike, a lamproite intrusion likely weathered for millennia but still intact at depth. This structure fit institutional lamproite dispersion models precisely, narrow, asymmetrical, and cloaked under residual soil. Its signature matched those from productive, if low-yield, fields in India's Bundelkhand Craton and Australia's Ellendale Field. In the end, it wasn't the sparkle that mattered most. Not the apparent heft, nor even the adamantine flash that first caught attention along the riverbank. It was the pattern, the coherent alignment of indicator minerals, the terrain logic, the tests that passed and failed, and the one fragment that held up under every challenge. And within that fragment, Small, colored, and now independently verified, lay something larger. Confirmation that deep geological systems still leave subtle surface traces, waiting for those who know how to read them. The discovery, ultimately, was twofold. Yes, a natural pink diamond fragment emerged from what had been considered a non-prospective context, a previously unmapped lamproitic zone marked by alteration, dense mineralogy, and a tectonic history compatible with plastic deformation. But the greater discovery was procedural, that even in a landscape full of false positives, simulants, and exhausted ground, it remains possible, with process, patience, and correct interpretation, to isolate something of real value. The breakthrough didn't rely on high-tech gear or deep funding. It came from methodical repetition, attention to subtle anomalies, and grounding in well-established institutional models.